Hey folks, Ms. Gosling here. Fair warning, this is going to be a bit of a long video because in this video we're going to be covering the nuts and bolts of graphing. And so by the end of the video, you need to be able to transition smoothly between position versus time graphs, velocity versus time graphs, and acceleration versus time graphs. So you're going to learn how to start at a position time graph, create the velocity and acceleration time graphs for that position time graph, and go back in the same direction. Um, so with no further ado, let's go ahead and jump right into things. Um, so on this slide, you can see a position versus time graph that I've created from the data on the left. And I created this graph by just plotting points. So my time is 0, so I plot 0 on the x-axis. My position is 0, 0 on the y-axis. At my time of 5, I have a point of 3. So you guys should be able to do this. I'm not going to go over how to draw these graphs. And when I create a position versus time graph, what I want to do is connect those dots. So I'm going to go ahead and try to do that as cleanly as I possibly can, like so. And that is simply how I'm going to graph position versus time. Once I have a position versus time graph, I can start calculating my velocity versus my time. Now, I know that velocity is defined as my change in position over my change in time, my displacement over my time. Looking at my graph, the change in position is the rise in my graph. It's how far up or down I go up or down the y-axis. From your math class, you probably have seen this written as your rise. Time is how far I go along the x-axis, which you may have seen written in a math class as your run. So velocity is equal to change in position over change in time, or the rise over run for my graph, otherwise known as the slope of my graph. So to find my velocity, what I want to do is break my position time graph up into places that have constant slope. So I can see that I have a straight line from 0 to 3 seconds, and at 4 seconds, from 3 to 4 seconds, and at 4 seconds I'm going to change velocity again and have a consistent velocity from 4 to 5 seconds. So I'm going to call these A, which I'm going to make red, B, which I'm going to go ahead and do in blue, or no, I'll do B in green, and C, which I'm going to go ahead and do in black. So to find out the slope for A, what I'm going to do is I'm going to pick point number 1, and that's going to be 0, 0. And point number 2, which I can see is at 3, 6, and I'm going to do my slope formula. So my slope, I'm going to call that VA, my velocity in section A, is y2 minus y1 over x2 minus x1, or more accurately, actually, using what is measured on my x and y axes, it's actually position 2, or x2, minus x1, over my final time minus my initial time, t2 minus t1. So my final position is 6 here, and my initial position is 0. My final time is 3, and my initial time is 0, giving me a velocity for these first 4 points of 2 meters per second. So for 0, 1, 2, and 3 seconds, my velocity is 2. Next, I'm going to look at the section from 3 to 4 seconds. So VB is equal to x2 minus x1 over t2 minus t1. I'm going to go ahead and use 3, 6 as my t1 x1, my initial point, and my final point is going to be here at 4, 3. So my final position is 3 and my initial position is 6. My final time is 4 and my initial time is 3. So again, positions and times, giving me a velocity of negative 3 meters per second. So for 3 and 4 seconds, I'm going to go ahead and write negative 3 as my velocity for both of those points. Finally, for my last few seconds, I have an initial point of 4, 3, and a final point of 6, 3. So my velocity is at C is going to be 3 minus 3 over 6 minus 3, x2 minus x1 over t2 minus t1, giving me a velocity of 0 meters per second. And in fact, you can recognize anytime you have a straight line like this, that means your velocity equals 0. So for 4, 5, and 6, I'm going to go ahead and write 0 into my table. So when I am graphing my velocity versus time graph, what I want to do is I want to take the velocities that I calculated and put in my table, and I want to just graph all of those points. So I can graph my initial velocity. So between 0 and 3 seconds, my velocity is 2. So I would want to draw dots at 2 on those points. At 3 seconds, my velocity kind of instantaneously is going to change to negative 3 meters per second. And so I want to draw that for both 3 and 4 seconds. And then at 4, I'm going to stop on a dime and my velocity becomes 0 and stays at 0 for my last 3 points. When I connect those dots, I get the blue line that you saw in this initial graph when I first switched to the slide. So that is how I'm going to transition from a position time graph to a velocity versus time graph. So now that I've created my velocity versus time graph, I can start working on finding my acceleration versus time graph. So I know that acceleration is defined. I'm going to go ahead and change my color here. I'm going to go ahead. I know that acceleration is defined as my change in velocity over my change in time. Now on my graph, my change in velocity is what's going on my y-axis. So in algebra terms, that is my rise, and my change in time is what's going on my x-axis. In algebra terms, that is my run. So my acceleration is the slope of a velocity versus time graph. And the way you can tell if you're calculating whether you're calculating velocity or acceleration is by looking at the title of the graph, which should tell you whether you're looking at a velocity versus time graph or a position versus time graph. If there isn't a title, you can also always look at the x-axis over here. I'm going to go ahead and get rid of some of my circles because I find them very distracting. So now that I have calculated, now I know if I want to calculate my acceleration, I need to find my slope. Just like I did in my first graph, what I'm going to do is I'm going to go ahead and break my graph up into chunks with consistent slope. So I have a constant slope from 0 seconds until 3 seconds. 3 seconds is kind of its own section, and so I'm going to kind of draw these like little weird dashes so you can see that. From 3 to 4 seconds, I have a constant slope. Again, at 4 seconds, I have a new slope. My line is not a straight horizontal line anymore. And from 4 to 6 seconds, I again have a constant slope. So I have 5 sections, which I'm going to go ahead and call A, B, C, D, and E. So section A, I'm going to go ahead and pick out my 2 points. So I start at 0, 2, and I end at 3, 2. So my acceleration at A is going to be my final velocity minus my initial velocity over my final time minus my initial time, which I can write as 2 minus 2 over 3 minus 0, or 0 meters per second squared, which I can write for 0, 1, 2, and 3 seconds. And in fact, every time I have a horizontal line, I know that that is a slope of 0. So for C and for E, I can write 0 as well. So C is 3 to 4 seconds, and E is going to be 4 to 6 seconds. That's yellow, excuse me. And so all my horizontal sections have a slope of 0. If I had a diagonal section, so if I had a section that looked, for example, like this, I would calculate that using my slope formula as well, like I just did in my previous video, or in the previous slide. Next, I have sections B and D to look at. And in section B, which I'm going to write up here, my velocity at B, I have an initial position of 3, 2, and I have a final position down here at 3, -3. So when I'm calculating my slope here, what I'm going to need to do is use my slope formula. VB is equal to -3 minus 2, V2 minus V1, over T2 minus T1, 3 minus 3. And that gives me a slope of -5 over 0. And you should remember from your math classes that dividing by zero gives me an infinite number. So I can actually write this as -infinity. And so from 3 to 0, so at 3 seconds, I have a slope of 0. Then I briefly am going to have a slope of -infinity, and then a slope again of 0. And so that's something that we call an asymptote. So we're going to asymptotically approach 3 and infinity, and then go back to 0. At 4, so section D, I am going to start at 4, -3, and I'm going to end at 4, 0. So my velocity at D is going to be -3 minus 0 over 4 minus 4. Or sorry, 0 minus -3 over 4 minus 4. My final velocity minus my initial velocity over my final time minus my initial time. That gives me a velocity of 3 over 0, or positive infinity. So for 4, I have an asymptote that is going to approach positive infinity. When I graph this, it's going to look like so. So at 3, from 0 to 3, I have a 0. And then I'm going to asymptotically approach infinity. Then we're going back down to 0. At 4 seconds, we're going to asymptotically approach positive infinity, go back down to 0, and finish our graph out at 6 seconds. And so my graph is going to look like this. If you were to simplify this graph and just draw a straight line, that would also be acceptable. However, the blue line is more accurate and therefore preferable. I'm going to go ahead and skip discussing how we go from an acceleration versus time to a velocity versus time graph. So what I want you to know is that the area under the curve for an acceleration versus time graph gives me my velocity versus time graph. So the same method I'm going to use here to go from velocity versus time to position versus time could be used to go from acceleration to velocity. However, the graph that I started with, the graph that we just drew, is not conducive to this assignment, so I'm going to go ahead and not do that example. However, you should know the same method I'm following here to go from velocity to position is the method you would use to go from acceleration to velocity. So looking at this graph, I can see that I have velocity on the y-axis and time on the x-axis. I know that velocity is equal to my change in position over my change in time. Therefore, my change in position is equal to velocity times my change in time, otherwise known as the area under my blue line, under my blue rectangle. More specifically, it's the area between the velocity, the line of the velocity versus time graph. So area between line and the x-axis. So this space that I'm about to color in black, that is all area under that line in the picture, but it is not what I'm going to use to calculate my position. I'm going to go ahead and undo that because I think it's confusing. So in this case, my change in position So I'm going to go ahead and show you there's clearly three shapes here that I know the equations to find the area of. I have A, B, and C here. So for A is in the shape of a rectangle. So I know that the equation for the area of a rectangle is base times height. So my change in position for A is equal to the base of my height of my rectangle times the height of my rectangle, or 3 times 2. Thus, my change in position over that period of time is 6 meters. So if I start at 0, 0, then at 3 seconds, I have reached 6 meters. In fact, I can see that I'm going at a speed of 2 meters per second. So after 1 second, I must have gone 2 meters. After 2, I'll have gone 4. And after 3, I'll have gone 6. If you don't want to have to think about it, the other way you can think about this is I'm going at a constant velocity over 3 meters. So I can do 6 divided by 3. Or sorry, I'm going at a constant velocity over 3 seconds. So if I end at positions, so that means that I should be going at a constant, that my change in speed every second should be consistent. So if I divide 6 divided by 3, I get 2. So that means every second I should go 2 additional meters. Another option is you can just use your endpoints in your table. So I could just not have this in my table, not have 1 second in my table. I could also not have 2 seconds in my table, and I could just plot 0, 0, and 3, 6 and draw a straight line between them. Similarly, I could get rid of 5 as well, which I'm going to go ahead and do now. So looking at area, so that's area A. Area B is going to show me my change in position between 3 seconds and 4 seconds. So the change in position over this period of time is again going to be base times height because this is a rectangle. If this was, for example, a triangle, like so if I had a blue line that looks like this, and I was looking at this area, my change in position would instead be 1/2 times base times height. But because we have a rectangle, we can use our base times height equation instead. So I'm going to go ahead and get rid of the triangle again, just to make this a little less confusing. So my change in position is base times height. My base is 1 second. My height is -3. So my base times height is going to be -3 meters. So between 3 and 4 seconds, I have gone backwards 3 meters. So my position after 4 is going to be my position at 3. So x at 4 is equal to x at 3 minus my change in, or plus my change in x. Or 6 plus -3, or 3 meters. So at 4 seconds, I'll be at my position of 3 meters. The way that I like to do this is I like to calculate delta x here. And then what I'll do is I'll look at where my previous number was, and I'll just add this number to that. So I'll do 6 plus -3 to give myself this number. Finally, I can go ahead and calculate my area for C. So my change in x for C, I'm going to go ahead and call this a rectangle. My base is 2 seconds, and my height is 0 meters per second. Therefore, my area is 0. Now, I'm not going to end up at position 0, right? What that means is that I'm going to add 0 to whatever was previously written. So plus 0, so 3 plus 0 is going to give me a position at 6 seconds of still 3 meters. Graphing that, I'm going to see the graph that is pictured here. So remember, I started at 0, 0. I ended at, from 3 to, in my first 3 seconds, I ended at 3, 6. Then I went backwards 3 meters, ending at 4, 3. Finally, I stood still, and so my position after 6 seconds was still 3 meters. So the only points I really need to graph are these 4 points, and then I can simply connect them in a straight line. And that is how I can use area to draw my position time graph based off of my velocity versus time graph. So a couple of takeaways. The way that I'm going to express these takeaways is a little different, as you can see. I'm going to use a table. So to go from a position versus time graph to a velocity versus time graph, I'm going to use slope. To go from a velocity versus time graph to an acceleration versus time graph, I also find slope. To go backwards, down from acceleration all the way down to position, so acceleration to velocity, I'm going to use area, and velocity to position, I will also use area. And that is how I can start with a position time graph, create an acceleration versus time graph, and then go back to my original position versus time graph. And there you have it, guys. You now know the basics of graphing. So it is your turn to give this a try on your own. Best of luck and happy solving.